Look up at the night sky right now. See all those stars? Every single one of them, plus all the galaxies you can't even see, adds up to less than 5% of what's actually out there in space. That means 95% of our universe is completely invisible to us. We can't see it, we can't touch it, and we barely understand what it is. Right now, you're sitting on a tiny rock, flying through space at incredible speeds, and that rock is part of something so huge that your brain literally cannot imagine how big it really is. Most people think space is just empty darkness with some stars scattered around. But the truth is far more mind-blowing than that. Today, I'm going to show you why the universe is bigger than anything you've ever imagined. Not just bigger in size, but bigger in ways that will completely change how you think about everything around you. We're going to explore invisible worlds, mysterious forces, and ideas that sound like science fiction, but are actually real science. By the time we're done, you'll never look at the night sky the same way again. Are you ready to have your mind blown? Because once you learn what I'm about to tell you, there's no going back to thinking small about the universe. Let's start with something that's going to surprise you right away. Most people think that if the universe is about 14 billion years old, then we should be able to see 14 billion light years in every direction. That makes perfect sense, right? Light has been traveling for 14 billion years, so it should reach us from 14 billion light years away. But here's the thing that's going to blow your mind. That's completely wrong. The part of the universe we can actually see is about 93 billion light years across. Yes, you heard that right. 93 billion light years, not 14 billion. So how is this possible? How can we see further than light has had time to travel? The answer is one of the most amazing things about our universe, and it's all about something called cosmic expansion. Imagine you're standing on one side of a huge balloon, and your friend is standing on the other side. Now imagine that balloon is being blown up really, really slowly. If your friend throws a ball to you while the balloon is expanding, that ball has to travel a much longer distance than when your friend first threw it. By the time the ball reaches you, your friend is much further away than when they started. This is exactly what's happening with light in our universe. When light left the most distant galaxies we can see, those galaxies were much closer to us. But while that light was traveling through space to reach us, space itself was expanding. It's not that the galaxies were moving away from us through space. Space itself was getting bigger, carrying those galaxies along with it. By the time that ancient light finally reaches our telescopes today, those galaxies are now much, much further away than they were when the light started its journey. Think of it like this. Imagine an ant walking across a piece of paper toward you. But while the ant is walking, someone is slowly stretching the paper, making it longer and longer. The ant keeps walking at the same speed, but because the paper is stretching, it takes much longer to reach you. And by the time the ant gets to you, the place where it started is much further away than it was when the ant began walking. This is why we can see light from galaxies that are now 93 billion light years away, even though the universe is only about 14 billion years old. The light has been traveling for nearly 14 billion years, but during that time, space has been expanding, stretching the distance between us and those distant galaxies. Now, let's talk about what this actually means in terms of size, because the numbers are so big that they become almost meaningless. Let's try to understand this by starting small and working our way up. If our entire Earth was shrunk down to the size of a marble, you know, those little glass balls you might have played with as a kid, then our solar system would be about 6 kilometers across. That's like the distance from one side of a small town to the other, just to put one solar system in perspective. Now, if we keep that same scale, our entire galaxy, the Milky Way, with all its hundreds of billions of stars, would be about as big as North America. The whole continent, every single star you can see in the night sky with your naked eye, is just in our tiny local neighborhood of this galaxy-sized continent. But wait, it gets crazier. At that same scale, the observable universe, that 93 billion light-year bubble around us, would be bigger than the orbit of Saturn. Just think about that for a moment. If Earth is a marble, the observable universe is bigger than Saturn's orbit. But here's what's really going to mess with your head. All of this unimaginably huge observable universe, might be just a tiny, tiny piece of what's actually out there. It's like looking at the ocean from the beach. You can see the water stretching to the horizon, and it looks enormous. But you know that the ocean continues far beyond what you can see. The observable universe is just our horizon in space. The edge of what we can observe isn't a real wall or boundary. It's just the limit of how far light has had time to reach us since the universe began. Beyond that boundary, space almost certainly continues. There are probably more galaxies, more stars, more planets, and maybe even more life. We just can't see them yet because their light hasn't had enough time to reach us. Scientists call this boundary the cosmic microwave background. It's like a glowing wall that surrounds us at the edge of the observable universe. But it's not really a wall. It's just the afterglow of the Big Bang itself. This is the oldest light in the universe, from when the universe first became transparent about 380,000 years after it began. Before this time, the universe was so hot and dense that light couldn't travel freely. It would get absorbed and scattered by all the particles floating around. It was like trying to see through a thick fog. But when the universe cooled down enough, that fog cleared, and light could finally travel freely through space. The cosmic microwave background is that first light, stretched and cooled by billions of years of cosmic expansion. What's amazing is that we can detect this ancient light with special telescopes. It's everywhere around us, coming from every direction in space. It's like the universe's baby picture, showing us what things looked like when the universe was just a tiny fraction of its current age. When scientists study this cosmic microwave background, they can learn incredible things about our universe. They can figure out how old it is, what it's made of, and how it has changed over time. They've discovered that our universe is flat, meaning that if you could travel in a straight line forever, you would never curve back to where you started. They've also confirmed that the universe is expanding faster and faster as time goes on. This brings us to something that should make you feel both very small and very special at the same time. Carl Sagan, the famous scientist and science communicator, once said something beautiful about our place in the universe. He called Earth a pale blue dot suspended in a sunbeam. He was talking about a picture taken by a space probe from the edge of our solar system, where Earth appeared as just a tiny speck of light. Sagan pointed out that everything that has ever happened in human history, every war, every love story, every scientific discovery, every work of art, all of it happened on that tiny speck. Every person who has ever lived, from ancient kings to modern celebrities, lived their entire lives on that pale blue dot. When you think about the scale of just our observable universe, Earth becomes almost impossibly small. But here's the special part. Despite being so incredibly tiny compared to the universe, we humans are the only things we know of that can actually understand how big the universe is. We're made of atoms that were forged inside dying stars billions of years ago. We are literally made of star stuff, as Sagan liked to say. And now, those atoms have organized themselves in such a way that they can look back out at the universe and figure out where they came from. We can measure distances to galaxies billions of light years away. We can figure out what stars are made of just by looking at their light. We can even detect the afterglow of the Big Bang itself. In a very real sense, we are the universe becoming aware of itself. Through us, the cosmos is discovering its own size, age, and history. The observable universe contains at least 2 trillion galaxies. Each galaxy contains hundreds of billions of stars. Many of those stars have planets orbiting them. The numbers become so large that they lose all meaning. There are more stars in the observable universe than there are grains of sand on all the beaches on Earth. And remember, this is just what we can see. The actual universe is almost certainly much, much larger. So when you look up at the night sky tonight, remember that you're not just seeing a few thousand stars scattered across the darkness. You're looking out into a cosmic ocean that stretches for 93 billion light years in every direction. You're seeing the light from galaxies so far away that their light has been traveling toward you since before Earth even existed. You're witnessing a universe so vast and ancient that it contains more worlds than there are thoughts in every human mind that has ever lived. And this is just the beginning of our journey into cosmic vastness. Now, we're going to explore something that will really challenge how you think about reality. Everything I just told you about the observable universe, that massive 93 billion light-year bubble around us, that's probably just a tiny fraction of what's actually out there. Think about that for a moment. The biggest thing you can possibly imagine, and it might be practically nothing compared to the whole universe. This brings us to one of the most mind-bending problems in all of science. It's called the horizon problem, and understanding it will change how you see everything around you. Remember when I compared the observable universe to standing on a ship in the middle of the ocean? You can see to the horizon in every direction, but you know the ocean continues beyond what you can see. Well, the same thing is happening with our universe, but it's much more complicated and much more amazing than you might think. The reason we can't see beyond our cosmic horizon isn't because there's nothing there. It's because there hasn't been enough time for light to travel from those distant places to reach us yet. Light is fast, incredibly fast, but it's not infinitely fast. It travels at about 300,000 kilometers per second. That sounds super fast, and it is. But when you're dealing with cosmic distances, even light takes time to get around. Here's what's really going to blow your mind. Every single day, our observable universe gets a little bit bigger. Not because the universe is expanding. Well, that's happening too. But because light from slightly more distant places finally has time to reach us. It's like the horizon around our ship is slowly moving outward, revealing new parts of the ocean that were always there, but just too far away to see before. But here's where it gets really crazy. Scientists believe that space continues far, far beyond what we can observe. How far? Well, it might go on forever, literally forever. An infinite universe with infinite galaxies, infinite stars, and infinite planets. Try to wrap your head around that for a second. If the universe is truly infinite, then every possible thing that could happen has happened somewhere. There are infinite versions of Earth out there. There are infinite copies of you living infinite different lives. There are infinite civilizations, infinite works of art, infinite everything. In an infinite universe, anything that's not impossible has happened not just once, but infinite times. Now you might be thinking, wait, how can scientists possibly know what's beyond what we can see? That's a great question, and the answer comes from some of the most brilliant minds in human history, starting with Albert Einstein. Einstein's theories of relativity tell us some amazing things about space and time. One of the most important ideas is called the cosmological principle. This basically says that on the largest scales, the universe looks pretty much the same everywhere. It's not like there's a special center with everything else arranged around it. No matter where you are in the universe, it should look roughly the same in all directions. Think of it like looking at the surface of the ocean from high above. From any one spot, the ocean looks pretty much the same in all directions. Waves, water, more waves, more water. The cosmological principle says that space is like this. No matter where you are, you should see galaxies and cosmic structures arranged in roughly the same patterns. This means that if we can see galaxies and cosmic structures stretching out to our horizon in every direction, then those same kinds of structures probably continue beyond our horizon too. It's like if you're flying over the ocean and you can see waves stretching to the horizon in every direction, you can be pretty confident that there are more waves beyond the horizon, even though you can't see them. But Einstein's theories tell us something even more amazing. Space itself might be flat and infinite. Imagine the surface of a perfectly flat table that goes on forever in all directions. That might be what space is like, except instead of 2 dimensions like a table, space has 3 dimensions. This infinite flat space would be filled with galaxies and stars and planets, stretching on forever. Now, there are other possibilities too. Space might curve back on itself like the surface of a ball. If you started traveling in one direction and kept going perfectly straight for long enough, you would eventually come back to where you started, just like if you walk in a straight line on Earth's surface. But when scientists measure the shape of space by looking at the cosmic microwave background, they find that space appears to be perfectly flat, at least as far as we can tell. A perfectly flat space that goes on forever is almost impossible to imagine, but that seems to be what we live in. And if that's true, then there are consequences that sound like science fiction, but might be real science. In an infinite universe, the laws of physics and chemistry work the same way everywhere. The same kinds of atoms exist, the same kinds of stars form, and the same kinds of planets develop. This means that somewhere out there, far beyond what we can see, there should be another galaxy, just like the Milky Way. And in that galaxy, there should be another star, just like our Sun. And orbiting that star, there should be another planet, just like Earth. In fact, if space is truly infinite, then there are infinite copies of Earth out there. Some of them are exactly like ours. Others are slightly different. Maybe on one of them, you decided to wear a different shirt today. On others, you chose a different career. Or you were never born at all. Or dinosaurs never went extinct. This sounds completely crazy. but it's actually a serious scientific idea. If you have infinite space filled with matter arranged randomly, then every possible arrangement will occur somewhere. It's just a matter of statistics. With infinite space and infinite time, everything that can happen will happen. But wait, there's more. Some scientists think our observable universe might be just one bubble in a much larger structure called the multiverse. Imagine blowing soap bubbles. Each bubble is separate from the others, but they're all part of the same foam. Our observable universe might be like one of those bubbles, floating in a vast foam of other universe bubbles. These other universe bubbles might have completely different laws of physics. In some of them, atoms might not be able to form. In others, gravity might be much stronger or much weaker than it is here. Most of these universe bubbles would be completely hostile to life as we know it. We exist in one of the rare bubbles where the laws of physics happen to allow stars and planets and life to develop. This idea comes from something called inflation theory. Right after the Big Bang, space expanded incredibly fast, much faster than the speed of light. This expansion was so violent and chaotic that different regions of space ended up with slightly different properties. Each region became its own universe bubble, and we happen to live in one of them. If this is true, then asking, how big is the universe, becomes almost meaningless. It's like asking, how big is the number line? The number line goes on forever in both directions, with infinite numbers. Similarly, the multiverse might go on forever in all directions, with infinite universe bubbles. But here's what's really amazing about all this. Even though we can't see beyond our cosmic horizon, we can still learn about what's out there. We can study the cosmic microwave background to understand the overall shape and structure of space. We can use Einstein's theories to predict what should exist beyond what we can see. We can build mathematical models of infinite space and see what kinds of structures should form. Scientists are also working on new ways to probe beyond our horizon. They're studying something called gravitational waves, ripples in space-time itself that travel at the speed of light. These waves might carry information from beyond our normal horizon. They're also looking for subtle effects in the cosmic microwave background that might tell us about the larger structure we're embedded in. The more we learn, the more obvious it becomes that our observable universe is just a tiny sample of something much, much larger. It's like examining a single drop of ocean water and trying to understand the entire Pacific. That drop can tell you a lot: what the water is made of, how salty it is, what kinds of microscopic life it contains. But it can't tell you about whales, or coral reefs, or underwater mountains, or the countless other wonders that exist in the vast ocean beyond. We are living in that single drop, trying to understand an ocean that might be infinite in size. Every night, when you look up at the stars, you're seeing just the tiniest fraction of what's out there. Beyond every star you can see, beyond every galaxy our telescopes can detect, space continues on and on and on, filled with wonders we can't even begin to imagine. And this is just the beginning of how big the universe really is. Now, we're going to take a journey that will stretch your mind in ways you never thought possible. We've talked about how big the universe is, but size isn't just about going bigger and bigger. The universe is also incredibly, unimaginably small at the same time. And when you start to understand both the biggest and smallest things that exist, you realize that reality is far stranger and more wonderful than anything you could have imagined. Let's start by going in the opposite direction from where we've been. Instead of zooming out to see galaxies and cosmic structures, let's zoom in. Let's go smaller and smaller until we reach the very limits of what size even means. You know what an atom is, right? Those tiny building blocks that make up everything around you, your body, the air you breathe, the device you're watching this on. Atoms are incredibly small. If you could line up atoms side by side, it would take about 10 million of them to stretch across the width of your thumb. That's already pretty hard to imagine. But atoms are made of even smaller things. Inside each atom, there's a nucleus made of protons and neutrons, with electrons zipping around it. The nucleus is so much smaller than the atom that if an atom was the size of a football stadium, the nucleus would be like a marble sitting at the center of the field. But we can go smaller still. Protons and neutrons are made of even tinier particles called quarks. And here's where things start to get really weird. According to our best theories, there might not be anything smaller than quarks. They might be truly fundamental, meaning they have no internal structure at all. But even if quarks are the smallest pieces of matter, space itself might be made up of even smaller units. At the tiniest possible scale, smaller than anything we can measure or even imagine, space might be made up of discrete little chunks. This is called the Planck length, and it's so small that it makes atoms look gigantic. How small is the Planck length? It's about 10, followed by 35 zeros smaller than a meter. To put this in perspective, if you could somehow expand an atom until it was as big as our entire observable universe, the Planck length would still only be about as big as a tree. Think about that. A tree compared to the entire observable universe. That's how much smaller the Planck length is compared to an atom. At this scale, the normal rules of physics break down completely. Space and time themselves become fuzzy and uncertain. Some scientists think that at the Planck scale, space is constantly bubbling and foaming, with tiny virtual particles popping in and out of existence faster than we could ever measure. This brings us to one of the strangest ideas in all of physics, string theory. According to string theory, everything, every particle, every force, every piece of matter and energy is made up of incredibly tiny vibrating strings. These strings are so small that they exist at the Planck scale. Different vibrations of these strings create different particles, kind of like how different notes on a guitar string create different musical sounds. But here's where string theory gets really mind-bending. For the math to work out, these strings can't just vibrate in our normal 3 dimensions of space. They need extra dimensions, possibly as many as 11 dimensions total. Where are these extra dimensions? They're curled up so small that we can't see them or feel them. At every point in our normal 3-dimensional space, there might be 6 or 7 additional dimensions rolled up smaller than the Planck length. Imagine an ant walking on a telephone wire. From far away, the wire looks like a one-dimensional line. But if you're the ant walking on it, you can also move around the wire's surface. That's a second dimension that only becomes obvious when you look closely enough. According to string theory, our universe might be like that telephone wire, with hidden dimensions that are too small for us to notice. If string theory is correct, then what we think of as fundamental particles are really just different ways that strings vibrate in these hidden dimensions. An electron is one kind of vibration, a photon is another, and so on. All the complexity and diversity of our universe, from galaxies to planets to life itself, comes from the simple fact that tiny strings can vibrate in different ways. This leads us to something even more incredible: the possibility that our entire universe is just one of countless others. Remember how I talked about the multiverse earlier? Well, there are actually several different ways that multiple universes could exist, and they operate at completely different scales. The first type of multiverse is just more space beyond what we can observe. If space goes on forever, then there are infinite regions like our observable universe, each with their own galaxies and stars and planets. This is mind-boggling enough, but it's actually the most conservative possibility. The second type comes from something called cosmic inflation. Right after the Big Bang, space expanded incredibly fast, much faster than the speed of light. But this expansion might not have happened uniformly everywhere. Different regions might have inflated at different rates, or stopped inflating at different times. Each region that stopped inflating became its own universe, like a bubble in cosmic foam. These universe bubbles would have completely different properties, different laws of physics, different types of particles, different values for fundamental constants like the strength of gravity. Most of these universe bubbles would be completely hostile to life. In some, matter might not be able to form atoms. In others, stars might burn out too quickly for planets to develop. We happen to live in one of the rare bubbles where the laws of physics are just right for complexity and life to emerge. But there's a third type of multiverse that's even stranger. It comes from quantum mechanics, the science of how particles behave at the smallest scales. According to one interpretation of quantum mechanics, every time a quantum event happens, every time a particle decides which way to spin or which path to take, reality splits into multiple versions. In one version, the particle spins one way. In another version, it spins the other way. Both versions are equally real. This means that there are infinite versions of you living infinite, slightly different lives. In some universes, you made different choices. In others, historical events happened differently. In still others, the fundamental laws of physics are different. All of these realities exist simultaneously, branching off from each other every time anything quantum happens, which is constantly, everywhere, at the smallest scales. The fourth type of multiverse is the most abstract, but possibly the most profound. Some scientists think that every mathematically possible universe actually exists as a physical reality. Our universe happens to follow the mathematical rules we call the laws of physics. But there might be other universes that follow completely different mathematical rules. Universes where geometry works differently, where logic operates in alien ways, where the very concept of space and time might not apply. If this is true, then mathematics isn't just a tool we use to describe reality. Mathematics is reality. Every equation, every mathematical structure, every logical possibility exists somewhere as a physical universe. We live in just one of these mathematical realities, trying to understand our own cosmic equation from the inside. Now you might be wondering, how could we ever know if any of this is true? How can scientists study things that are smaller than we can measure, or universes that we can never visit? The answer is that we look for indirect evidence and mathematical consistency. For example, we can't see individual strings from string theory but we can test whether string theory makes predictions that match what we observe in particle accelerators. We can't visit other universe bubbles, but we can look for their gravitational effects on our cosmic microwave background. We can't directly observe quantum parallel universes, but we can test whether quantum mechanics really works the way the theory predicts. The amazing thing is that the more we learn about both the very large and the very small, the more connected they seem to be. The same quantum processes that happen at the Planck scale might have determined the structure of the entire observable universe during cosmic inflation. The properties of tiny strings might determine whether galaxies can form. The mathematics that describes parallel universes might also explain why our universe has the properties it does. What's really incredible is that we humans, made of atoms that are made of particles that might be made of vibrating strings in hidden dimensions, can even begin to understand any of this. We're like characters in a cosmic story trying to read the book we're living in. We're using brains made of star stuff to figure out the rules that govern everything from the smallest quantum foam to the largest cosmic structures. Every time you look around you, remember that you're seeing just the middle layer of reality. Zoom in far enough, and you'll find a quantum wonderland where particles tunnel through walls and exist in multiple places at once. Zoom out far enough, and you'll find cosmic structures so vast that our entire observable universe might be just a tiny bubble in infinite space. And if the most mind-bending theories are correct, there might be infinite versions of you in infinite universes, all made of the same vibrating strings, all following the same quantum rules, all part of the same magnificent mathematical reality that we're only just beginning to understand. The universe isn't just bigger than you imagine. It's bigger and smaller and stranger and more wonderful than anything you could possibly imagine. Now, I'm going to tell you something that should completely change how you think about everything around you. Everything you can see, touch, and interact with. Your body, the earth, the sun, all the stars in the sky, all the planets we've discovered, every galaxy we've ever observed. All of this makes up less than 5% of the universe. Less than 5%. That means 95% of everything that exists is completely invisible and mysterious to us. This isn't science fiction. This isn't speculation. This is one of the most well-established facts in modern astronomy, and it's based on decades of careful observations and measurements. We live in a universe that is mostly made of things we can't see and don't understand. Let me explain how we discovered this invisible universe and what it means for everything we thought we knew about reality. The story begins in the 1970s with a brilliant astronomer named Vera Rubin. She was doing something that sounds pretty simple, measuring how fast galaxies spin. Just like you can measure how fast a record player spins, she wanted to know how fast entire galaxies rotate around their centers. Now, this might seem like a boring thing to study, but Rubin expected to find something very specific. According to everything we knew about gravity and physics, stars on the outer edges of galaxies should move more slowly than stars near the center. This is exactly what happens in our solar system. Planets closer to the sun move faster than planets farther away. Mercury zips around the sun much faster than Neptune does. But when Rubin actually measured galaxy rotation speeds, she found something completely shocking. The stars on the outer edges of galaxies were moving just as fast as stars near the center. Some were even moving faster. This should have been impossible. These galaxies should have torn themselves apart. The stars on the outside should have been flung off into space long ago. There was only one way to explain what Rubin was seeing. There had to be much more matter in these galaxies than anyone could see. Invisible matter that was providing the extra gravitational pull needed to hold the fast-moving outer stars in orbit. Without this invisible matter, galaxies simply couldn't exist. At first, astronomers hoped this invisible matter might just be normal stuff that was hard to see. Dim stars, planets, gas clouds, black holes. They called these things dark matter just because they were dark and hard to detect. But as they studied the problem more carefully, they realized that even if you added up all the dim stars and black holes you could possibly have, it still wasn't nearly enough. There had to be something else out there, something completely different from any kind of matter we'd ever encountered. Today, we know that this mysterious dark matter makes up about 27% of the entire universe. It's everywhere around us right now. There are dark matter particles streaming through your body as you watch this video. Billions and billions of them pass through you every second, but they barely interact with normal matter at all. They don't absorb light. They don't emit light. They don't bounce off things the way normal particles do. The only way we know they exist is through their gravitational effects. Think about that for a moment. More than a quarter of everything that exists is made of particles we can't see, can't touch, and barely understand. It's like discovering that most of the ocean is filled with invisible fish that you can only detect by the way they disturb the water around them. But as mind-blowing as dark matter is, it's not even the strangest part of this story. The strangest part came in 1998, when two teams of scientists were studying distant exploding stars called supernovas. They were trying to measure how the expansion of the universe was slowing down over time. You see, everyone expected the expansion to be slowing down. After the Big Bang, the universe started expanding rapidly, but all the matter in it should be pulling back on itself with gravity, gradually slowing that expansion. The question was just how much it was slowing down, and whether it would eventually stop expanding and start contracting again. But when these scientists actually measured distant supernovas, they found something that nobody expected. The expansion of the universe wasn't slowing down at all. It was speeding up. The universe was expanding faster and faster as time went on. This discovery was so shocking that the scientists who made it won the Nobel Prize. But it raised a huge question. What could possibly be pushing space apart faster and faster? What kind of force could overcome all the gravity in the universe and accelerate cosmic expansion? The answer, as far as we know, is something called dark energy. And dark energy is even more mysterious than dark matter. While dark matter at least behaves somewhat like normal matter, it clumps together under gravity and helps form the cosmic structures we see. Dark energy seems to be a property of space itself. Dark energy makes up about 68% of the universe. Combined with the 27% that's dark matter, this means that the normal matter you're familiar with, atoms, molecules, everything you can see and touch, represents less than 5% of reality. Let me put this in perspective with a simple analogy. Imagine you thought you understood your neighborhood pretty well. You know all the houses, all the people, all the streets and shops. But then you discover that for every house you can see, there are about 5 invisible houses that you never knew existed. And for every person you know, there are about 19 invisible people walking around that you can't detect. That's essentially what we've discovered about our universe, the cosmic web, those vast structures of galaxies stretching across billions of light years that we talked about earlier, is actually just the visible scaffolding of a much larger invisible structure. The dark matter was there first, forming invisible webs and filaments throughout space. Normal matter then fell into these dark matter structures, like decorations being hung on an invisible Christmas tree. Without dark matter, none of the cosmic structures we see today could have formed. After the Big Bang, the universe was very smooth and uniform. There were tiny density fluctuations, places that were just slightly more dense than others. But these small differences wouldn't have had enough time to grow into galaxies and galaxy clusters using just normal matter and gravity. Dark matter saved the day because it doesn't interact with light or normal matter very much. While normal matter was being pushed around by radiation pressure in the early universe, dark matter was quietly clumping together under its own gravity. By the time normal matter was free to start forming structures, dark matter had already built the invisible framework that normal matter could fall into. This means that every galaxy, including our own Milky Way, is embedded in a much larger halo of dark matter. Our galaxy contains about 100 billion stars, but it's surrounded by a dark matter halo that's probably 10 times more massive than all those stars combined. Right now, as Earth orbits the Sun, we're also moving through this invisible dark matter ocean that surrounds our galaxy. Scientists have built incredibly sensitive detectors trying to catch dark matter particles directly. These detectors are buried deep underground to shield them from cosmic rays and other interference. They're waiting for the moment when a dark matter particle finally interacts with normal matter in just the right way to be detected. So far, despite decades of searching, we haven't caught one. But we can map where dark matter is by studying how it bends light. This effect is called gravitational lensing. Just like a glass lens can bend light rays, massive objects can bend light with their gravity. When we look at distant galaxies through regions of space that contain a lot of dark matter, those galaxies appear distorted and stretched. By studying these distortions, we can create maps of where the dark matter is, even though we can't see it directly. These maps reveal something amazing. Dark matter forms a vast cosmic web, with dense filaments connecting massive nodes where galaxy clusters form. It's like looking at the skeleton of the universe, the invisible structure that everything else is built on. Dark energy is even more puzzling than dark matter. The best explanation we have is that it's a property of empty space itself. According to quantum mechanics, even completely empty space isn't really empty. It's filled with virtual particles that pop in and out of existence so quickly that we can't detect them directly. These virtual particles might create a kind of pressure that pushes space apart. But here's the problem. When scientists try to calculate how much dark energy there should be based on quantum mechanics, they get an answer that's bigger than what we actually observe by a factor of about 10 to the power of 120. That's not just wrong. It's the most wrong prediction in the history of science. We're missing something fundamental about how the universe works. What makes this even more mysterious is that dark energy seems to be perfectly constant throughout space and time. No matter where you look in the universe, or how far back in time you observe, the density of dark energy appears to be exactly the same. This is very strange because as the universe expands, normal matter and dark matter get more spread out and less dense. But dark energy density stays the same, which means that as space expands, more dark energy appears to fill the new space. The future of our universe depends entirely on dark energy. If dark energy continues to accelerate the expansion of space, then eventually galaxies will move so far apart that they disappear beyond each other's horizons. Stars will burn out and not be replaced. The universe will become cold, dark, and empty. But we don't know if dark energy will remain constant forever. It might change over time. It might even reverse direction and start pulling the universe back together again. Without understanding what dark energy actually is, we can't predict the ultimate fate of everything that exists. Some scientists think dark energy might be evidence that our three-dimensional space is actually embedded in higher dimensions, just like string theory predicts. The expansion we observe might be caused by gravitational effects from these higher dimensions that we can't directly perceive. Others think dark energy might be a sign that Einstein's theory of gravity breaks down on cosmic scales. Maybe we need a completely new understanding of how gravity works over vast distances. What's truly humbling is that we've discovered we don't understand 95% of the universe we live in. It's like realizing that most of your house is invisible to you, or that most of your friends are people you can't see or hear. We're surrounded by mystery on the largest possible scale. But here's what's amazing about this situation. Even though we can't see dark matter or understand dark energy, we know they exist because of their effects on the things we can observe. Science has given us the tools to detect the invisible, to map the unseeable, and to study the unknowable. Every time you look up at the night sky, remember that you're seeing less than 5% of what's actually there. The rest is hidden in plain sight, surrounding you, supporting the cosmic structures you can see, and determining the fate of everything that will ever exist. We are truly living in a universe far stranger and more mysterious than our ancestors could have ever imagined. To truly appreciate just how vast and strange our universe actually is, we need to understand how completely wrong humans have been about the cosmos throughout most of our history. The journey from our ancestors' tiny, Earth-centered universe to today's understanding of infinite space filled with dark matter and multiple dimensions is one of the most dramatic transformations in human thinking. For thousands of years, humans looked up at the same night sky you see today, but they saw something completely different. They didn't see a universe billions of light years across, filled with trillions of galaxies. They saw a small, cozy cosmos with Earth sitting right at the center of everything. Let's go back about 2,000 years to ancient Greece, where some of the smartest people who ever lived were trying to figure out how the universe worked. Aristotle, one of history's greatest thinkers, created a model of the cosmos that seemed to make perfect sense at the time. He put Earth at the center of everything, surrounded by a series of crystal spheres that carried the moon, the sun, the planets, and the stars around us. In Aristotle's universe, everything had its proper place. Heavy things like rocks fell toward the center because that's where they belonged. Light things like fire and air rose upward because that was their natural direction. The heavenly bodies moved in perfect circles because circles were the most perfect shape. It was a universe that felt orderly, understandable, and designed specifically for human beings. This wasn't just Aristotle's personal opinion. It became the accepted truth for over 1,000 years. When you combine Aristotle's ideas with the detailed mathematical model created by Ptolemy, you get a picture of the universe where Earth is the most important place. Humans are the most important creatures, and everything in the cosmos revolves around us, literally. How big was this ancient universe? Tiny by today's standards. The entire cosmos, from Earth to the outermost sphere of stars, was thought to be smaller than what we now know is just our solar system. All the stars were thought to be the same distance from Earth, stuck to the inside of a giant crystal sphere, like decorations on the inside of a snow globe. Beyond that sphere of stars, there was simply nothing at all. But even in ancient times, some people suspected the universe might be bigger than it appeared. A Greek astronomer named Aristarchus proposed that the sun, not Earth, was at the center of the cosmos. He even tried to measure the distances to the sun and moon, though his methods weren't accurate enough to get the right answers. Another Greek thinker, named Democritus, suggested that the Milky Way might be made up of countless distant stars, and that there might be other worlds beyond our own. These ideas were too radical for their time. Most people found it much easier to believe in a small, Earth-centered universe where humans were clearly the most important beings in creation. This view dominated human thinking for well over 1,000 years. Through the fall of the Roman Empire, the rise of Christianity and Islam, and into the medieval period, medieval scholars, both Christian and Islamic, refined and expanded on the ancient Greek model, but they didn't fundamentally change it. The universe was still seen as a series of crystal spheres centered on Earth, though now these spheres were thought to be moved by angels rather than by natural forces. The entire cosmos was contained within what they called the primum mobile, the outermost moving sphere, beyond which lay the realm of God. This medieval universe was not just small, it was also young. Based on biblical chronology, scholars calculated that the entire universe had been created only a few thousand years earlier. Everything that had ever existed or would ever exist was contained within a cosmic bubble that you could walk across in a few months. And the whole thing had been running for less time than recorded human history. Then came the Renaissance, and everything began to change. In 1543, a Polish astronomer named Nicholas Copernicus published a book that would revolutionize human thinking forever. Copernicus proposed that the sun, not Earth, was at the center of our cosmic system. The planets, including Earth, orbited around the sun, and Earth was just one planet among many. This might not sound like such a big deal to you, since you've known since childhood that Earth orbits the sun. But try to imagine how shocking this idea was to people who had spent their entire lives believing that Earth was the center of everything. Copernicus wasn't just changing astronomy. He was suggesting that humans weren't as special or as central to creation as they had always believed. At first, most people rejected Copernicus's ideas. They seemed to go against common sense. If Earth was spinning and moving around the sun, why didn't we feel that motion? Why didn't objects get left behind as Earth moved through space? It took decades for these objections to be answered satisfactorily. The real breakthrough came when Galileo Galilei pointed the first telescope at the sky in 1609. What he saw changed everything. The moon had mountains and craters. It wasn't a perfect celestial sphere, as everyone had believed. Jupiter had moons orbiting around it, proving that not everything in the cosmos orbited Earth. The sun had spots on it that moved, showing that it rotated, Most importantly, when Galileo looked at the Milky Way through his telescope, he saw that it was made up of countless individual stars. Suddenly, the universe became much, much bigger. Instead of a few thousand visible stars stuck to the inside of a crystal sphere, there were millions of stars at vastly different distances. Some stars were relatively close, others were incredibly far away. The cosmos was no longer a cozy sphere surrounding Earth. It was a vast ocean of space filled with more stars than anyone had ever imagined. But even Galileo couldn't have guessed how vast space really was. For the next 300 years, astronomers gradually discovered just how big our cosmic neighborhood actually is. They learned that stars were actually suns like ours, but so far away that they appeared as tiny points of light. They discovered that our sun was just one of hundreds of billions of stars in a vast collection called the Milky Way galaxy. Isaac Newton made the next great leap in understanding. His law of universal gravitation showed that the same force that makes apples fall from trees also keeps planets in orbit around the sun and holds the entire universe together. Newton realized that if gravity worked the same way everywhere, then the universe might be infinite, filled with infinite stars held in balance by their mutual gravitational attraction. This was a staggering idea. An infinite universe meant infinite worlds, infinite possibilities, infinite everything. Newton's cosmos was so large that the human mind could barely begin to comprehend it. And yet, as vast as Newton's universe was, it was still much smaller than what we know today. Throughout the 1800s and early 1900s, astronomers continued to discover that the universe was bigger than they had thought. They realized that some of the fuzzy patches of light they could see through telescopes weren't just nearby clouds of gas. They were actually entire galaxies, each containing billions of stars, located unimaginably far away. But even Einstein, the greatest physicist of the 20th century, initially got the universe wrong. When Einstein developed his theory of general relativity, he believed the universe was static, neither expanding nor contracting, just sitting there unchanged for all time. When his equations suggested the universe should be either expanding or contracting, Einstein added a mathematical term called the cosmological constant to keep his universe static. Einstein later called this cosmological constant his greatest blunder, because observations soon showed that the universe really was expanding, just as his original equations had predicted. The person who proved the universe was expanding was Edwin Hubble. In the 1920s, using the most powerful telescope in the world, Hubble made two earth-shattering discoveries. First, he proved that those fuzzy patches of light really were separate galaxies, each containing billions of stars. Second, he showed that these galaxies were all moving away from us, and the farther away they were, the faster they were receding. This could only mean one thing: the universe was expanding. Space itself was getting bigger, carrying the galaxies along with it, like raisins in a rising loaf of bread. If the universe was expanding now, that meant it must have been smaller in the past. Follow this logic back far enough, and you get to a moment when everything in the universe was compressed into an infinitely hot, infinitely dense point. This was the beginning of what we now call the Big Bang Theory. Suddenly, the universe had not just size, but history. It wasn't eternal and unchanging, as philosophers had assumed for thousands of years. It had a beginning. It was evolving, and it might even have an end. The cosmos became a dynamic, changing entity with its own life story. Throughout the latter half of the 20th century, astronomers continued to push back the boundaries of the known universe. They discovered quasars, incredibly bright objects powered by supermassive black holes billions of light years away. They found the cosmic microwave background radiation, the afterglow of the Big Bang itself. They measured the age of the universe at about 13.8 billion years and its observable size at about 93 billion light years across. But just when astronomers thought they were getting a handle on the universe, they discovered dark matter and dark energy, revealing that 95% of the cosmos was made of completely unknown stuff. They found evidence for cosmic inflation, suggesting our observable universe might be just a tiny bubble in an infinitely larger multiverse. Today, we know we live in a universe that's not just bigger than our ancestors imagined, it's bigger than they could have possibly imagined. The tiny Earth-centered cosmos that satisfied humans for thousands of years has given way to a reality of infinite space, parallel universes, and mysterious invisible forces that dwarf anything in our experience. What's remarkable is how recent this transformation has been. Your great-great-grandparents probably grew up thinking the Milky Way was the entire universe. Your grandparents lived through the discovery that space was expanding and had a beginning. Your parents witnessed the discovery of dark matter and dark energy. In just a few centuries, we've gone from thinking we lived in a small cosmos centered on Earth to realizing we inhabit an possibly infinite multiverse, where our entire observable universe might be smaller than an atom compared to the whole of reality. This journey isn't over. The universe continues to reveal new layers of vastness and strangeness that challenge everything we thought we knew about existence itself. Right now, as you're watching this, we're living through one of the most exciting periods in the history of astronomy. Every few months, scientists are making discoveries that completely change our understanding of how big and strange the universe really is. We have telescopes and instruments that would seem like magic to astronomers from just a few decades ago, and they're revealing cosmic mysteries that are even more mind-blowing than anything we've talked about so far. The most famous of these new tools is the James Webb Space Telescope, which launched in 2021 and started sending back images in 2022. This isn't just a bigger version of older telescopes. It's a completely revolutionary way of looking at the universe. While the Hubble Space Telescope mostly sees visible light, the James Webb Telescope sees infrared light, which allows it to peer through cosmic dust and look further back in time than we've ever been able to before. And what it's showing us is absolutely incredible. The James Webb Telescope has found fully formed galaxies that existed when the universe was only about 400 million years old. That might sound like a long time, but in cosmic terms, it's like finding a fully grown adult when you expected to see a newborn baby. These ancient galaxies are much more massive and organized than our theories predicted they should be at such an early time in the universe's history. This discovery is forcing scientists to completely rethink how quickly structures could form in the early universe. It's like finding a modern city in what you thought was an empty wilderness. Some of these early galaxies contain supermassive black holes with billions of times the mass of our Sun, and we have no idea how they could have grown so large so quickly. The telescope is also finding planets around other stars that are even more diverse and strange than we expected. We've discovered planets made of diamond, planets where it rains molten glass sideways, planets that orbit their star so closely that their surfaces are hot enough to vaporize metals. Some planets are so large they blur the line between planets and failed stars. Others are so small and dense they might be the exposed cores of gas giants that had their atmospheres stripped away. But perhaps the most exciting discovery is how common potentially habitable planets appear to be. The James Webb Telescope can analyze the atmospheres of distant planets by studying how starlight filters through them. We're finding water vapor, oxygen, and other chemicals that might indicate the presence of life on worlds hundreds of light years away. Meanwhile, a completely different kind of astronomy is revolutionizing our understanding of the universe. For the first time in human history, we can now detect gravitational waves, ripples in the fabric of space-time itself. These waves are created when incredibly massive objects, like black holes or neutron stars, collide and merge. Before we could detect gravitational waves, it was like we were deaf to half the universe. We could see cosmic events with telescopes, but we couldn't hear them. Now, we have a completely new sense that allows us to study the universe in ways that were impossible just a decade ago. The Laser Interferometer Gravitational Wave Observatory, or LIGO, has detected dozens of black hole mergers since it first started operating. Each detection tells us something new about these mysterious objects. We've learned that black holes are much more common than we thought, and they come in a wider range of sizes. We've detected mergers between black holes that are dozens of times more massive than our Sun, creating even more massive black holes in the process. But the most exciting gravitational wave detection so far was the collision between two neutron stars in 2017. This event was detected not just by gravitational wave detectors, but also by traditional telescopes around the world. For the first time, scientists could study a cosmic event using both light and gravitational waves simultaneously. What they found was incredible. The collision created a massive explosion called a kilonova that forged heavy elements like gold and platinum. In fact, scientists now think that most of the gold in your jewelry and electronics was created in neutron star collisions like this one. You're literally wearing pieces of cosmic catastrophes that happened billions of years ago. These neutron star collisions might also help solve one of the biggest mysteries in cosmology, the Hubble tension. This is the fact that when we measure how fast the universe is expanding by looking at nearby objects, we get a different answer than when we measure it using the cosmic microwave background. This disagreement suggests that either our measurements are wrong or there's something fundamental about the universe that we don't understand. Gravitational waves from neutron star mergers provide a completely independent way to measure cosmic expansion. As we detect more of these events, we might finally resolve this mystery and discover whether we need new physics to explain how the universe works. Another frontier that's expanding rapidly is the search for exoplanets, planets orbiting other stars. We've now confirmed the existence of over 5,000 exoplanets, and new ones are being discovered almost daily. But we're not just finding these planets. We're learning incredible details about what they're like. Some exoplanets are so close to their stars that they're tidally locked, with one side permanently facing the star and the other side permanently dark. The day side of these planets can be hot enough to melt rock, while the night side can be colder than anything on Earth. Between these extremes, there might be a narrow band where temperatures are just right for liquid water, and possibly life. We've found planets orbiting binary star systems, where inhabitants would see two suns in their sky, like in Star Wars. We've discovered planets that orbit their stars backwards, planets with orbits so stretched out that they experience extreme seasonal changes, and planets that are being slowly devoured by their dying stars. Perhaps most intriguingly, we're starting to detect biosignatures, chemicals in exoplanet atmospheres that might indicate the presence of life. Oxygen, water vapor, and methane in the right combinations could be signs that an alien world hosts living organisms. While we haven't definitively found life beyond Earth yet, several planets are showing promising signs that we're investigating further. One of the most exciting recent developments is the discovery of potentially habitable planets around red dwarf stars. These stars are much smaller and cooler than our Sun, but they're also much more common, and they live for trillions of years. Planets in the habitable zones around red dwarf stars would experience very different conditions than Earth. They might be tidally locked or experience frequent solar flares, but some scientists think they could still support life. If life can exist around red dwarf stars, then the number of potentially habitable worlds in our galaxy increases dramatically. Instead of a few billion Earth-like planets, there might be hundreds of billions of worlds where life could develop. At the same time, we're making incredible progress in understanding the large-scale structure of the universe. New surveys are mapping the positions of billions of galaxies, revealing the cosmic web in unprecedented detail. We're seeing how dark matter filaments connect galaxy clusters across billions of light years, and how vast cosmic voids separate these structures. These surveys are also helping us understand dark energy better. By measuring how the cosmic web has evolved over billions of years, we can track how dark energy has influenced the expansion of space. Some recent observations suggest that dark energy might not be perfectly constant over time, which would have profound implications for the ultimate fate of the universe. We're also making progress on one of the biggest mysteries in physics: the nature of dark matter. While we still haven't directly detected dark matter particles, new experiments are getting closer to the sensitivity needed to find them. Underground detectors are becoming more sophisticated, and particle accelerators are creating conditions that might produce dark matter particles artificially. At the same time, astronomical observations are revealing more about how dark matter behaves on cosmic scales. We can now map the distribution of dark matter around galaxy clusters with incredible precision, and we're finding that its behavior matches our theoretical predictions remarkably well. But perhaps the most mind-bending frontier in modern cosmology is the search for evidence of the multiverse. While we can't directly observe other universes, there might be indirect ways to detect their existence. Some scientists are looking for patterns in the cosmic microwave background that might be created by collisions between our universe and neighboring ones. Others are searching for anomalies in the distribution of matter that might indicate we live in a universe with unusual properties. Still, others are developing ways to test whether the fundamental constants of physics could have different values, which would be evidence for the kind of multiverse predicted by inflation theory. We're also using quantum experiments to test some of the stranger predictions of physics. Scientists are creating quantum entanglement between particles separated by increasingly large distances, testing whether quantum mechanics really works the way our theories predict on macroscopic scales. All of these discoveries are happening right now in your lifetime. We're living through a golden age of cosmology where new telescopes, detectors, and experiments are revealing the universe to be even stranger and more wonderful than we ever imagined. Every month brings new discoveries that challenge our understanding of reality itself. The universe is not just bigger than we thought. It's actively revealing new layers of bigness and strangeness that we never knew existed. And we're probably just getting started. The next decade will bring even more powerful telescopes, more sensitive gravitational wave detectors, and more sophisticated experiments that will continue to expand our understanding of just how vast and mysterious the cosmos really is. We are truly living in the most exciting time in human history to be curious about the universe. Now that we've explored just how incredibly vast and strange the universe really is, we need to ask ourselves a fundamental question. What does all of this mean for us? How should we think about our lives, our problems, our hopes and dreams when we exist in a cosmos that might be infinite, filled with invisible matter and energy, and possibly containing countless other universes? This isn't just an academic question. Understanding our place in the universe has profound implications for how we see ourselves, how we treat each other, and how we think about the meaning and purpose of human existence. The cosmic perspective can be both humbling and inspiring, terrifying and comforting, all at the same time. Let's start with the most obvious implication. We are incredibly, almost impossibly small. When Carl Sagan called Earth a pale blue dot, he was trying to help us understand just how tiny our world is compared to the cosmos. But even Sagan, brilliant as he was, couldn't have fully grasped the scale we understand today. Think about it this way. If you took every human who has ever lived, all the great leaders, all the brilliant scientists, all the artists and writers and philosophers, all the ordinary people living ordinary lives, and you added up all their thoughts, all their experiences, all their loves and fears and dreams, the entire story of human civilization would still be confined to a speck of dust in a universe that might be infinitely large. Every war that has ever been fought, every empire that has ever risen and fallen, every discovery that has changed the world, every work of art that has moved people to tears, all of it has happened on this one tiny planet, orbiting an ordinary star in the suburbs of an ordinary galaxy that is one of trillions in the observable universe alone. This perspective can be overwhelming. It can make human life seem meaningless and insignificant. Why should anything we do matter if we're just temporary arrangements of atoms on a cosmic speck that will eventually be consumed by our dying sun? Why should we care about human problems when the universe is so vast and indifferent to our existence? But there's another way to look at this cosmic perspective, and it's actually quite the opposite. Yes, we are small, but we are also incredibly special. As far as we know, we are the only part of the universe that has become aware of itself. We are atoms that have learned to contemplate atoms. We are the universe discovering its own vastness. Think about how extraordinary this is. After nearly 14 billion years of cosmic evolution, after countless generations of stars lived and died, after planets formed and were destroyed, somehow the universe produced beings capable of understanding their own cosmic context. Through us, the cosmos is asking questions about itself. Through us, the universe is experiencing wonder, curiosity, and the desire to understand. This brings us to one of the most profound questions in all of philosophy. Are we alone? In a universe that might contain infinite planets, orbiting infinite stars, it seems almost impossible that Earth is the only world where life has developed. The numbers are just too vast. Even if the chance of life developing on any given planet is incredibly small, with infinite or near infinite opportunities, life should exist in countless places throughout the cosmos. This is often called the Fermi paradox, named after physicist Enrico Fermi, who famously asked, "Where is everybody?" If the universe is so vast and old, and if life is even remotely common, we should see evidence of other civilizations everywhere. We should detect their radio signals, their spacecraft, their massive engineering projects. The sky should be buzzing with activity from countless alien civilizations. But we see nothing. The universe appears to be eerily silent. This silence becomes even more mysterious when you consider the cosmic scale. If just one civilization in our galaxy had developed the ability to travel between stars and colonize other worlds, they could have spread throughout the entire galaxy in just a few million years, a blink of an eye in cosmic time. There are many possible explanations for this silence. Maybe life is much rarer than we think. Maybe intelligence almost never develops. Maybe advanced civilizations tend to destroy themselves before they can spread to other worlds. Maybe they exist, but are so advanced that we can't recognize their activities. Maybe they're deliberately hiding from us. Or maybe we really are alone, at least in our cosmic neighborhood. This possibility is both terrifying and wonderful. Terrifying because it means we carry an enormous responsibility. We might be the only conscious beings in this part of the universe, the only entities capable of understanding and appreciating the cosmic story. If we destroy ourselves, we might be silencing the only voice the universe has ever produced. But it's also wonderful because it makes us incredibly precious. Every human life, every human thought, every human creation becomes infinitely valuable if we are truly rare in the cosmos. We are not just observers of the universe. We might be its only observers, at least locally. This leads us to what philosophers call the anthropic principle. This principle asks why the universe seems to be so perfectly designed for life. The fundamental constants of physics, things like the strength of gravity, the mass of the electron, the speed of light, all seem to be set to exactly the right values to allow stars to form, planets to exist, and life to develop. Change any of these constants by even a tiny amount, and the universe would be completely different. Make gravity slightly stronger, and stars would burn out too quickly for life to evolve. Make it slightly weaker, and stars might never form at all. Make the strong nuclear force a little different, and atoms couldn't exist. The universe seems to be balanced on a knife's edge that makes complexity and life possible. There are several ways to explain this apparent fine-tuning. One possibility is that there really is some kind of design or purpose behind the universe, that the constants were set by some cosmic intelligence specifically to allow life to develop. This is appealing to many people, but it raises the question of who or what could have done such a thing. Another explanation comes from the multiverse theories we discussed earlier. If there are infinite universes with different physical constants, then of course we find ourselves in one of the rare universes where life is possible. We couldn't exist in any other kind of universe to observe it. This is like a lottery winner being amazed at their luck. But someone had to win. and only the winner is around to be surprised. But regardless of why the universe allows life to exist, the fact remains that we are here. We are conscious, and we are capable of understanding our cosmic context. This gives us both tremendous responsibility and tremendous opportunity. The responsibility comes from recognizing that consciousness and intelligence might be incredibly rare in the universe. If we are among the few beings capable of understanding the cosmos, then we have an obligation to preserve and expand that understanding. We have a duty to explore, to learn, to push the boundaries of knowledge, and to ensure that conscious beings continue to exist in the universe. This perspective can completely change how we think about our everyday problems. Yes, your personal struggles are real and important to you, but they exist within a cosmic context that is almost unimaginably vast and ancient. The universe has been evolving for nearly 14 billion years to produce the atoms in your body, the planet you live on, and the consciousness that allows you to worry about your problems. This doesn't mean your problems don't matter. It means they matter within a larger framework of cosmic evolution and cosmic responsibility. You are not just a random collection of atoms. You are the universe becoming aware of itself, and that awareness is precious beyond measure. The opportunity comes from recognizing that we are part of something much larger than ourselves. We are connected to every star in the sky through the atoms in our bodies. We are connected to every living thing on Earth through billions of years of shared evolution. We are connected to the entire cosmic web through the fundamental forces that govern all matter and energy. This cosmic perspective can be incredibly liberating. Many of the things that cause us stress and anxiety, social status, material possessions, petty conflicts, become much less important when viewed against the backdrop of cosmic space and time. At the same time, the things that really matter, love, knowledge, beauty, the continuation of consciousness in the universe, become much more precious. Some people find the cosmic perspective terrifying because it makes them feel insignificant. But I think it should have the opposite effect. In a universe that might be infinite and eternal, the fact that you exist at all is miraculous. The fact that you can think about the universe, appreciate its beauty, and work to understand its mysteries makes you one of the most remarkable things that has ever happened in cosmic history. Carl Sagan put it beautifully when he said, "We are a way for the cosmos to know itself." Through human consciousness, the universe is exploring its own nature, questioning its own existence, and marveling at its own complexity. We are not separate from the cosmos. We are part of it, and perhaps its most amazing part. This cosmic perspective should fill us with both humility and pride. Humility because we are so small compared to the vastness of space and time. Pride because despite our small size, we are capable of understanding and appreciating that vastness. We are the universe's way of experiencing wonder, and that makes us cosmically significant, no matter how physically small we might be. When you look up at the night sky, remember that you are not just observing the universe, you are the universe observing itself. We've taken an incredible journey together through the vastness of reality, and I hope your mind is thoroughly blown by what we've discovered. Let's take a moment to step back and think about everything we've learned, because the truth about our universe is so extraordinary that it deserves to be absorbed slowly and appreciated fully. When we started this journey, I asked you to imagine that everything you could see in the night sky represented less than 5% of what's actually out there. Now you know that was just the beginning of the story. The universe isn't just bigger than you imagined. It's bigger in ways that stretch the very limits of what the human mind can comprehend. We discovered that our observable universe, that mind-boggling sphere, stretching 93 billion light years in every direction, might be just a tiny bubble in something infinitely larger. Beyond our cosmic horizon, space probably continues forever, filled with infinite galaxies, infinite stars, and infinite worlds. If that's true, then there are infinite copies of you living infinite variations of your life right now. But the universe's vastness isn't limited to the incredibly large. We explored how reality extends into dimensions so small that they make atoms look gigantic. At the Planck scale, space and time themselves might break down into quantum foam, where the normal rules of physics cease to apply. We learned about string theory's suggestion that everything might be made of tiny vibrating strings in 11 dimensions, most of which are curled up too small for us to perceive. We discovered multiple types of multiverse, from the simple continuation of space beyond our horizon to cosmic inflation, creating infinite universe bubbles with different laws of physics, to quantum mechanics potentially creating infinite parallel realities branching off from every quantum event. If any of these theories are correct, then the word big becomes completely inadequate to describe the scope of existence. Perhaps most humbling of all, we learned that everything we can see, touch, and interact with, every star, every planet, every living thing, represents less than 5% of the universe. The other 95% is made up of dark matter and dark energy, invisible forces and particles that we can detect only through their gravitational effects. We are swimming in an ocean of mystery, barely aware of the invisible currents that surround us and shape our cosmic destiny. We traced how human understanding of the universe has evolved from the tiny Earth-centered cosmos of our ancestors to today's picture of infinite space filled with parallel universes and hidden dimensions. In just a few centuries, we've gone from thinking the entire universe was smaller than our solar system to realizing we might live in something infinitely vast and strange. And we're still discovering new layers of cosmic vastness. Right now, as you watch this, the James Webb Space Telescope is finding galaxies that shouldn't exist. Gravitational wave detectors are hearing the universe's heartbeat, and scientists are closing in on the nature of dark matter and dark energy. Every few months brings new discoveries that expand our understanding of how big and mysterious reality really is. But here's what I find most remarkable about all of this. Despite learning how incredibly small we are in the cosmic scheme of things, we haven't become less significant. We've become more significant. We are the universe's way of understanding itself. Through human consciousness, the cosmos is exploring its own vastness, questioning its own nature, and marveling at its own complexity. Think about what an extraordinary thing this is. After almost 14 billion years of cosmic evolution, after countless stars lived and died, after planets formed and were destroyed, somehow the universe produced beings capable of comprehending infinity. We are arrangements of atoms that can contemplate the multiverse. We are cosmic dust that has learned to wonder about its origins. Every time you look up at the night sky and feel a sense of awe and wonder, you are participating in one of the most remarkable phenomena in the known universe: matter becoming aware of itself. The atoms in your brain, forged in the nuclear furnaces of dying stars billions of years ago, are now contemplating the very processes that created them. This cosmic perspective should fundamentally change how we think about our lives and our problems. Yes, we are incredibly small compared to the vastness of space and time. Every human worry, every achievement, every civilization that has ever existed is confined to a tiny speck in what might be an infinite cosmos. But this doesn't make our lives meaningless. It makes them precious beyond measure. In a universe that might be filled with infinite worlds, consciousness and intelligence might still be incredibly rare. We might be among the few arrangements of matter that have achieved self-awareness. If that's true, then every human thought, every moment of consciousness, every act of love or creativity or discovery represents something almost impossibly valuable in the cosmic context. The fact that we can understand even a fraction of cosmic reality makes us remarkable. The fact that we can feel wonder at the night sky, ask questions about our origins, and work together to unravel the mysteries of existence makes us cosmically significant, regardless of our tiny physical size. This perspective can be both humbling and inspiring. Humbling, because it reminds us that our everyday concerns exist within a context so vast that it boggles the mind. Inspiring, because it reveals that we are part of something magnificent, not separate observers looking at the universe from the outside, but integral parts of a cosmic story that has been unfolding for nearly 14 billion years. When you're stressed about work, or worried about relationships, or frustrated with the state of the world, remember the cosmic perspective. These concerns are real and important to you, but they exist within a framework of space and time that is almost unimaginably vast and ancient. The universe has been evolving for billions of years to produce the very atoms that make up your body and the consciousness that allows you to worry. This doesn't diminish your problems. It places them in context. It reminds you that you are part of something much larger and more wonderful than any individual concern. It suggests that consciousness and intelligence, wherever they occur in the universe, are precious beyond measure and worth preserving and celebrating. At the same time, the cosmic perspective can inspire us to think bigger and aim higher. If we are truly rare in the universe, then we have a cosmic responsibility to preserve and expand consciousness and intelligence. We have a duty to explore, to learn, to push the boundaries of knowledge, and to ensure that aware beings continue to exist in the cosmos. This means supporting space exploration, scientific research, and education. It means working to solve the problems that threaten human civilization: climate change, nuclear weapons, social inequality, not just for our own sake, but for the sake of consciousness itself in the universe. The humbling truth is that we know almost nothing about the universe we inhabit. Despite all our scientific advances, despite all our telescopes and particle accelerators and theoretical frameworks, we understand only about 5% of reality. The other 95% remains mysterious. We don't know if space is infinite. We don't know if other universes exist. We don't know what dark matter and dark energy are. We don't know if we're alone in the cosmos. But this ignorance is not a cause for despair. It's a cause for excitement. We are living in the early stages of cosmic exploration. Future generations will look back on our time as the era when humanity first began to glimpse the true scope of reality. They will see us as the pioneers who took the first tentative steps into an infinite ocean of discovery. The universe is bigger than you imagined, stranger, than you could have conceived, and more wonderful than you dared to hope. But you are part of it, and through you, it is coming to know itself. In a cosmos that might contain infinite wonders, you are one of those wonders, a temporary arrangement of star stuff that has learned to contemplate its own cosmic significance. So the next time you look up at the night sky, remember everything we've learned together. Those points of light are not just distant suns. They are members of a cosmic community that stretches across billions of light years and possibly into infinite dimensions. You are not just an observer of this cosmic dance. You are a participant in it, connected to every star through the atoms in your body and the consciousness in your mind. The universe is vast beyond imagination, but you are part of its grandest achievement, the emergence of beings capable of understanding that vastness. That makes you cosmically important, no matter how small you might feel in the face of infinity. If this journey through cosmic vastness has expanded your mind and filled you with wonder, I have a favor to ask. First, hit that subscribe button and ring the notification bell to join our community here at the Lazy Cosmos, where we explore the biggest questions about existence itself. Every subscriber helps us reach more curious minds and spread the cosmic perspective to people who need to hear it. Share this video with someone who loves to think about big questions. Maybe it's a friend who stares at the stars, a family member who wonders about our place in the universe, or just someone who needs to be reminded of how amazing it is that we exist at all. These conversations about cosmic scale and meaning are some of the most important we can have as conscious beings in a vast universe. And here's something really important. Support the scientists and space agencies who are working right now to expand our understanding of reality. Whether it's NASA, SpaceX, or the brilliant researchers at universities around the world, they are our species' way of reaching out into the cosmos and bringing back knowledge that expands human consciousness. What aspect of cosmic vastness blows your mind the most? Let me know in the comments below. Are you fascinated by the possibility of infinite parallel universes? Amazed by dark matter and dark energy? Wondering about what lies beyond our observable horizon? I read every comment, and your questions often inspire future videos here at the Lazy Cosmos. Remember, in a universe this vast and mysterious, curiosity is our greatest tool, and wonder is our greatest gift. Keep looking up, keep asking questions, and never stop marveling at the incredible fact that you exist in a cosmos far grander than anyone ever imagined. The universe is waiting to be explored, and you are part of that exploration. Thank you for taking this mind-expanding journey with me. Until next time, this is the Lazy Cosmos, reminding you that you are made of star stuff, and that makes you cosmically awesome.